And then it's my great pleasure to introduce the second speaker of this session, Arthur Hebecker. So Arthur is professor at Heidelberg University and specializing in string theory and currently investigating problems to the string landscape. And I have to say that there's a story to this talk, so it will be given virtually. So having had Corona in the past, it felt like going back to really these dark periods when I received the message that I cannot come, I caught an infection, but luckily he will be able to present this talk through Zoom, and then seeing that everything works, I'm happy to give the floor to you. Thank you.
Okay, thank you very much for the very nice introduction. And my apologies that my voice is bad, and my apologies that I cannot come in person. But please, can you confirm that my slides are visible and I can be heard more or less well?
Yes, we can confirm. We hear you well. The slides are on the screen. Everything is working.
Okay, okay. They are full screen, right? And you can see my mouse also.
Yes, we can also see you.
Okay, perfect. All right. So I want to give you basically a brief discussion of two issues which I find interesting in the broad context of string landscape and swampland. This is, on the one hand, the landscape itself and the question about the sitter vacuum, and then Cobordism and wormholes. So let me start with the outline. I don't want to assume that everybody knows the string theory landscape. So I will give you a brief reminder of the basics. And then I will come to the recent swampland debate and the subsequent scrutiny of accepted constructions of sitter models like KKLT and LVS. And finally, I will come to a few other swampland-related issues, namely wormholes and Cobordism conjecture, which are quite speculative, but I think are nevertheless very interesting. All right, so let's start. So there's an almost unique starting point, which is, of course, the hallmark of string theory, namely the worldsheet theory with two-dimensional supergravity embedded in d dimensions. I have drawn here the famous picture where a string propagates and, for example, splits into two further strings, and a particle splits into two particles. On the string worldsheet, you have the fields which describe its embedding in spacetime and also fermionic partners. So this theory is very easily defined and then has an enormous richness of solutions. Crucially, the theory works only in 10 dimensions, a number which is then uniquely fixed. And there it produces an almost unique 10-dimensional effective theory. So now I basically go in 10 dimensions still to the low energy effective theory. And it turns out that there are several of them which are related by dualities, which I will not describe, but there's a more or less unique 10-dimensional field theory Lagrangian, which I will call type 2b supergravity. I will focus on that branch. And I want to be technical in describing the landscape, so I want to give you the 10-dimensional Lagrangian, or the action. It is written here. There's a prefactor, which is basically 1 over the string coupling squared, the ancient Hilbert term, then various kinetic terms for the dilaton, which governs the string coupling, and for various form fields, here from H3 to F135. These are just higher form gauge fields, basically. And then crucially, and we'll come back to that, there's a so-called Chern-Simons term. There you have a wedge product between some of these forms. So now let's go on towards the string theory landscape. And I will first start, as I promised, to review what is maybe well known to most string theorists, but as I said, I will not necessarily assume that everybody here knows that. So the first step is, of course, one wants to go from 10 dimensions to 4 dimensions. I mean, on the one hand, one should emphasize this is a beautiful theory of quantum gravity in 10 dimensions, but it's far from trivial whether this is something to do with the real world, which is a 4-dimensional quantum gravity. So the first step is to solve the vacuum equations of motion, compactifying from 4 dimensions, from 10 dimensions to 4 dimensions on Calabi-Yau's. So the reason to choose Calabi-Yau's is this solution of equation of motion, because they are Ricci-flat, so the Einstein equations is automatically solved without adding any further ingredients. More precisely, we consider geometries which are R1, 3 for our 4D spacetime times X, and X will be, that's why I said more precisely, Calabi-Yau divided by some discrete group K. It is called, this quotient is called Calabi-Yau orientifold. In this quotient thing, there's also an orientation change of the string world sheet, so that's why orientifold, but that's not crucial for us. What's crucial is that the geometry on which you compactify the compact space now ceases to be smooth. I give you a simple example of this, a simple visualization. Let's take a torus T2 and divide it by Z2. It's easy to convince yourself that what comes out is this kind of geometry, which now does not have any more the topology of a torus, but of a sphere, but it has in particular 4 conical singularities, which are in the context of string theory would be called orientifold planes. And the dimension of the orientifold planes may vary from 03 to 07. This will be the most important ones for us. So 3 and 7 here stand for the spatial dimension. This is a 4 or 8 dimensional defect. And right, so it's important to keep in mind that we have Calabi-Yau's with such defects introduced by orientifolding, which will play an important role in the following. So I continue still with the discussion of the basics of string landscape. So now we obtain a 4D effective field theory. And in particular, this 4D effective field theory will include the so-called moduli, the moduli of the Calabi-Yau orientifold X. And moduli, I mean massless, exactly massless fields, flat directions, which describe the geometry, the change of the geometry of that manifold. Here there are 2 different types, which is again a key standard part of the string landscape, namely by Z, I denote the complex structure moduli. They basically describe the size of the relative size of 3 cycles. And T are the Kähler moduli. They describe the relative size of 2 and 4 cycle volumes and the total volume. There's a label of them. For them, there can be several, or there usually are several, in fact, very many for typical Calabi-Yau. The next key step is to introduce quantized fluxes. In other words, field strengths of the 3-form fields F3 and H3. These field strengths are quantized in the very same way as a standard electrodynamic field strength, a 2-form F2 would be quantized if you consider it on a 2-cycle, just by the standard charge quantization or precisely flux quantization condition. So these are switching on or turning on these field strengths correspond to a choice of discrete numbers, which you may consider to be part of the choice of geometry. And so basically we encode this into a set of vectors, Fi and Hi. And they induce a superpotential, which I will call W of Z, and which here is the product of these vectors F and H. There are some prefactors involving the fields C0 and the dilaton, and crucially multiplied by a further vector, the so-called period vector, pi of Z, which encodes the features of the Calabi-Yau. These are complicated special functions describing the particular Calabi-Yau under consideration. So from the superpotential, you then can derive a scalar potential, as the formula is given here. It's maybe not so crucial for those who know supergravity. It's very familiar. For the others, it's not so essential. There's a well-defined description how to get the scalar potential. And the scalar potential is such that generically stabilize all the complex structure moduli Z in terms of the chosen fluxes, Fi, Hi. So now comes a key point to do with the Chern-Simons term I mentioned before. This Chern-Simons term results in the following fact. The flux F3H3 plays the role of a source for the field strength F5. And so do the orientifold planes. They also source this F5. This is a non-trivial result of the 10-dimensional theory, the study of which I will not describe, but it is a very straightforward prediction. So basically, one then has something like a Gauss law constraint. I mean, there's a zero result from the integral of d star F5 just by Stokes theorem. And this d star F5 is the sum of the sources, and the sources are these fluxes, more precisely the wedge product of F3 and H3, and the localized sources, which are precisely those orientifold planes. Let me call the two contributions N and Q, and these two contributions, N plus Q, have to give zero. This is just an absolutely hard constraint on the consistency of the theory, or of the compactification. So in other words, the flux that I can turn on is limited by the tedpole contribution J local of the O planes. One can write this N in terms of these previous flux vectors like F times H, and the contribution of the O planes is given here. It is the sum of 1/4 times the number of O3 planes. Those are just points in the compact space, and so there's no geometry of them. And 1/2 times the Euler number of the O7 planes. These O7 planes are 8-dimensional, so they span 4-dimensional surfaces in the Calabi-Yau, and so their Euler number is what enters here. And the result of this, this possibility of switching on fluxes, but also the constraint of how much flux you can switch on, leads to the crucial fact that the landscape is huge, enormous. You know these numbers, a to the 500 or even more, that people discuss in various contexts, but it is finite. Nevertheless, crucially, it is finite. So then, at this point, Kähler moduli are still flat directions. And in the simplest case, there's just one Kähler modulus, which is the volume. And so to discover the potential of the Kähler moduli, one needs to study the model with more precision. One needs to consider so-called Euclidean D3 branes wrapped on 4 cycles instanton directions. These are not really branes present in the compactifications, but quantum fluctuations of such branes out of nothing. These instanton corrections change the superpotential I previously described by an E exponential correction factor, which is small but nevertheless crucial. Moreover, one needs to introduce, to go to a regime where the W0, this flux-induced potential, is small, and in this case, one can see that the scalar potential now changes in such a way that it is dependent on the Kähler moduli, and there's an ADS minimum. This construction of a fully stabilized ADS minimum is known as step 1 of the so-called KKLT construction. Step 2 involves the so-called uplifting to the sitter, which is of course crucial to describe our real world, or even to describe Minkowski, because this ADS is much too deep to be anything similar to our real world. This is done by adding anti-D3 branes, but it also requires a strongly warped region of so-called Klebanov-Schwarzschild throat to avoid destabilization. So this is now quite non-trivial. I mean, it's not too non-trivial, but for the talk, there's very little time to really explain that. So one has to do the following. One has to introduce a large amount of flux on an appropriate conifold region of the Calabi-Yau. As a result of this metric, which is dx squared for the 4 dimensions plus dy Calabi-Yau squared, the Calabi-Yau metric, is changed by a so-called warping factor. So there is now a prefactor here and here, which depends on the Calabi-Yau internal dimensions and the position in the Calabi-Yau. And the geometry is not anymore a direct product of external space and Calabi-Yau. And here in the picture, it is symbolized as this kind of extended region throat where the Calabi-Yau is kind of blown to a large, this region of the Calabi-Yau is kind of blown up to larger size. There's a redshift introduced to the anti-D3 brain, which breaks supersymmetry and gives you a positive energy density. Has a small effect, and this allows control and allows to avoid destabilization of the whole space, nevertheless uplifting you to the sitter. So if everything works, the picture is such that one first has this ADS minimum, then adds a positive contribution and gets a metastable de Sitter minimum, a very fine-tuned and delicate construction. One has to admit that full explicitness has remained elusive since finding fluxes which lead to W0 much smaller than 1 is extremely hard. We are searching here an exponentially large landscape. And also this actual anti-D3 brain in the strongly warped region is controlled only in 10 supergravity. It is not really controlled using supersymmetry or full string theory. So it's a difficult calculation which has not become fully explicit maybe. So now, based on this, these difficulties, the following situation has emerged. So this and some more important variants like LVS, which I will mention later, have remained the main evidence for stringy de Sitter. So these constructions are complicated and hard to get in an explicit fashion. And it has been proposed that maybe stringy de Sitter is simply impossible as a matter of principle. This is part of the Swampland discussion. And also many people have raised the concern that maybe de Sitter as such is a sick situation from the perspective of quantum gravity, and it should not be possible to get de Sitter space in a consistent quantum gravity theory. So subsequently, due to these conjectures, it has come to a new or very careful scrutiny of this KKLT and LVS constructions. And people have tried to question these constructions, and with varying success. And I will discuss now some of these points, which are focusing on what I think is most critical. So one issue that has, oh, sorry, I apologize, I have gone too far. So one issue is the so-called singular bulk problem. So I remind you, the situation is we have this Calabi-Yau with a throat with an anti-D3 brain glued in, which allows for the uplift. And this is a picture for how the potential is modified. So now it turns out that one has here the interplay of two small effects. On the one hand side, this exponentially small depth of the ADS minimum. On the other side, this uplift, which is exponentially small due to a large throat flux in the exponent, which governs the strength of this uplift effect. So it turns out that the matching between these two contributions implies that the throat, this strongly warped region, can actually not be parametrically smaller than the bulk. So one actually comes to a slightly bizarre situation when here there is the Calabi-Yau, here is the throat, but the situation must be even worse than that. The throat has to be larger than the Calabi-Yau. Now this leads to the result that this warp factor H, which I give you here again, which I introduced before, has to vary significantly, even in the so-called bulk or Calabi-Yau region. And it turns out that this unavoidably leads to the fact that this warp factor, in fact, goes negative in part of the bulk. So there is a situation when basically, since there is a square root here, the metric simply breaks down in a significant part of the Calabi-Yau, and one loses calculational control. That does not mean that the scenario KKLT is dead, but it's just not possible to generically claim that one has control of this analysis. So now there's a further version of this, LVS large volume scenario, which is a closed cousin of KKLT, with a crucial twist that the volume there is exponentially large. I will not explain how this largeness arises from the stabilization procedure. I can mention that Ignatius, who gave the previous talk, has an interesting alternative proposal. There's interesting work going on in this direction. I will focus on the classical LVS. And it turns out that this exponentially large volume, however, is not sufficient to save us from these previously discussed problems. In fact, as pointed out by Junghan some time ago, higher order curvature corrections in this 10-dimensional action, like r squared, r cubed, and so on. In fact, I'm simplifying here for the sake of this talk. The key terms are on the branes, and there's an r to the 4 term in the bulk. Let me not go into too much detail. These higher curvature terms nevertheless lead to potential loss of control. And as it turns out, control can be maintained if a sufficiently large D3 tadpole is available. The D3 tadpole is precisely this contribution from the O-planes which I had before. So this is an equality which we already know. You remember that there's this N from the flux, which is separated into the bulk flux and the throat flux, and has to be smaller than the maximal available Q. This is a geometric contribution from the O-planes, which is basically a feature of the geometry, which you can't play around with. It's given to you in terms of the Calabi-Yau's that you are using, of which there are finitely many as far as we know. So basically, one would want the contribution and bulk from the fluxes in the bulk to be small, because one already needs a lot of flux here in the throat to make the throat deep enough. And so together, it turns out that this situation becomes worse in view of higher curvature corrections in the throat, since controlling those enforces very large and throat, as I described before. So as a result, given that the known geometries have limited Q max, one wants to stabilize all complex structure moduli with as small a bulk tadpole and bulk as possible. However, there has recently been raised the possibility, or has been suggested, that a so-called tadpole conjecture holds, which claims exactly this to be impossible. It claims that if some flux vector stabilizes a large number n of complex structure moduli, then n flux has to be bigger than alpha times n, with alpha being an order 1 number. So if you have many complex structure moduli, which generically you want to have for the sake of having a large landscape, then you need a lot of flux. This conjecture has several strong and weaker forms. I will not discuss them in detail. There's also been the discussion of certain counterexamples, in particular to the stronger forms. And there's an ongoing debate about this conjecture, the quality of control issues for KKLT and LVS, as well as efforts to find geometries with a large Q max, this O-plane contribution to the tadpole. So this is the very interesting and controversial situation about the sitter in the string theory landscape. So now, for the last bit of the talk, I will turn to something completely different, namely, also in the context of landscape, Cobordism. So just forget what I said before, focus on a new topic. Very simple topic. Two manifolds of dimension d are cobordant if they form the boundary of a manifold of dimension d plus 1. So, for example, obviously by this picture, an S1 is cobordant to two S1s, and S1 is also cobordant to nothing. In normal, in this case, two-dimensional gravity, but this obviously extends to other dimensions. Now comes the so-called recently raised Cobordism conjecture. It says that in quantum gravity, all Cobordism groups are trivial. In other words, everything is cobordant to everything. One of the key arguments for this very strong conjecture is based on the no global symmetries conjecture, which is one of the most sacred Swampland conjectures. I will not discuss in detail the derivation and the arguments. Well, it's not really a derivation, it still remains a conjecture, but there's good supporting evidence. And there's a general underlying feeling that quantum gravity should allow any geometry to change into any geometry. So let's accept the Cobordism conjecture. The implications of this are very strong and very non-trivial. For example, it predicts new defects or new branes. So think of this picture here. If the spin bundle of this over this S1 here is trivial, then of course, naively, there's no such Cobordism, right? Because if you have here the boundary of a disk topologically, then the spin bundle on this S1 would not be trivial. There would be a 360-degree turn. So if you want an S1 with a trivial spin bundle to be cobordant to nothing, which according to the conjecture should be the case, then you need a new type of brane, which somehow gets rid of this spin twist. So it actually, this conjecture actually predicts new objects. Moreover, and this is another obvious implication, you cannot avoid the creation of baby universes. So basically a spacetime can emit a sphere. I draw here 2 dimensions, but you should think, of course, of our real world. I mean, a 4-dimensional spacetime can emit a 3-sphere as an extra baby universe, or 2 of them, and so on. Now, this baby universe story is, of course, a very old story. It goes back to getting Strominger, Coleman, Preskill. Coleman's original analysis allowed us to save us in this context from the apparently horrible non-locality that is introduced, namely by rewriting this whole baby universe summation or wormhole summation in terms of alpha parameters. So a baby universe being emitted and absorbed corresponds to such a wormhole geometry, and summing over all such wormhole geometry gives you this exponentiation, but then you can rewrite it like this using an alpha parameter, and the integral over alpha will reintroduce this non-local expression, but in this form here, it's a perfectly local theory, but there is a new parameter somehow introduced which describes the, roughly speaking, baby universe state, which is adjacent to our spacetime, which exists in addition to our spacetime. Now, recently, there has been some interesting new discussion and progress here. There has been a celebrated toy model by Marlow and Maxfield, who were able to explicitly solve by introducing also connections of 3 or more such wormholes, explicitly solve in 2 dimensions this summation. And this Marlow-Maxfield toy model turns out to have an unexpected reduction of the Hilbert space. Namely, it turns out that there's a gauge invariance which has to be modeled out, and the Hilbert space of this baby universe, this extra freedom in addition to our spacetime, is much smaller than expected. Now, on this basis, it has been conjectured that in D equals 4, this reduction is so strong that the Hilbert space of baby universes or alpha parameters becomes even one-dimensional, such that there's basically no such unwanted extra freedom in addition to our spacetime. Which, by the way, this freedom, as you maybe can see from this picture here, from this formula here, this freedom corresponds to coefficients of operators, which then become dependent on the baby universe state. So this is a very controversial story, has remained, so many others have struggled with the question whether string theory really possesses these underlying wormhole solutions. I listed a few of the authors who worked on this over the recent years, and in particular also very recently. And let me emphasize why it is for some people so important to get rid of these baby universes. A key problem is that even after Coleman's resummation, which apparently turns things local, this fundamental underlying non-locality still clashes with the locality of ADS-CFT, which, as you know, for string theorists thinking about quantum gravity is kind of a sacred assumption. So here is a picture, a sketch of what I want to tell you. This is the ADS space, this is the CFT living on the boundary. The fact that you have wormholes here clashes with the locality of the CFT on the boundary. So on the other hand, there's the recent success of wormholes in the black hole entropy context. For example, for the derivation of the island formula suggests that wormholes are really relevant. So this whole wormhole baby universe theory remains mysterious because there are strong arguments both in favor and against the physicality of these baby universes and the baby universe state. So you can find the recent literature by following these relatively recent papers by Marov-Maxfield and McNamara-Wafa. That brings me to the end. I hope I have not been too much over time. So string theory remains a leading candidate for fundamental theory of quantum gravity. The realistic landscape of flux vacuum, the SUSY breaking, and positive cosmological constant has come under pressure due to doubts raised in the Swampland debate. On the positive side, this has led to a new precision error in the construction of explicit string compactifications. The old story of Euclidean wormholes and baby universes has seen a revival due to the prominent role of wormholes in the black hole entropy context. And explicit toy models and new ideas for avoiding the problematic implications of the baby universe state are being discussed at this very moment. Thank you very much.
So thank you for delivering this great talk. It was a pleasure to listen to here from the audience. Are there questions? Daniele.
Yeah, thanks for the talk. Can you say something more about the clash between the wormhole story and the locality in ADS?
Yes. So if you introduce the alpha parameters to describe, to resum these, so basically you have to have your ADS bulk and you have to add in all these wormholes. And then you write the story in terms of the sum over the alpha parameters, as I gave you before. Look at this here, right? Then it turns out that you basically are arriving at a situation when it looks as if you have an integral over alphas, and for each value of the alpha, you have separate CFT. But you want the quantum gravity, or maybe you want the quantum gravity, it has also been the opposite conjecture, by the way, maybe you want the quantum gravity to be dual to one CFT. At least that is what one naively expects in the ADS CFT context. And so basically, having the alpha parameter somehow corresponds to what people have also called an ensemble average ADS CFT, which maybe is really the case in 2 dimensions in the context of SYK, but this is a special case which one does not really want to hold in 4 dimensions. I mean, it's simply open whether one should somehow get rid of the wormholes or reinterpret how they are included in quantum gravity, or whether one maybe very, courageously should claim that ADS CFT is only an ensemble average statement, so that the dual is not one CFT, but a sum of many CFTs weighted in a certain way by the alpha parameters. Does that answer the question?
Yes, there are more questions, and probably much more questions that we can take at the moment. So Sumati, and then we take 2 here.
Just a quick question, which is with these cobordisms, when this conjecture says that in quantum gravity that the cobordism is the group is trivial. We know that in the Lorentzian case, there are restrictions because not every 4-manifold or n-manifold admits a Lorentzian metric. So are these statements within the Lorentzian context or for Riemannian signature spaces?
Well, one has to honestly admit that these are statements, this is a physics conjecture. This is, of course, not a mathematics conjecture. I mean, it's clear that this, for example, let's go back to the simplest picture. It's clear that on this geometry here, one does not really have a smooth Lorentzian metric. So in string theory, where this diagram is typical, this is not a problem because one usually does these calculations in a Euclidean setting. But the Cobordism conjecture states that there must be really a physical process. I mean, the statement is, by saying the Cobordism groups are trivial, is that there's really a physical transition between this situation and this situation. So I mean, we all know that this is a famous problem, this absence of a Lorentzian metric, but the claim is that due to quantum gravity, it should be possible to transit from one geometry to another. I mean, if I had time, which I think I don't have, I could explain why, if I don't have such transitions, then it's easy to construct a situation where you basically have something akin to a non-decaying particle or non-decaying defect, which is not protected by gauge symmetry. So that should not be the case. And therefore, one simply proposes that this process is possible. But the calculation then, of course, goes as one usually does by transition to Euclidean and then some form as analytic continuation. But I totally admit that this is a quite open question, and it's of course possible that this is wrong and topology change is strictly forbidden, at least in such cases. I am not going to make a very strong statement. I'm just saying this is something which is very hotly debated at present.
Okay. Then the last question for the session. You can just pass it through.
Yeah, so are these wormholes supported by any topological charge? I guess axion charge, right? Is it necessarily only the axion charge?
Very good point. Yeah. So I, for time reasons, I skipped the fact that for these wormholes, for example, this one, there's explicit solutions. Gidding Strominger calculated this solution for the case that there is basically an axionic charge flowing through this wormhole. So roughly speaking, if you cut it transversely, there's a three-sphere, and you have the dual field strength F3 quantized on this transverse cut, which is a three-sphere. That supports the wormhole and makes it a solution. But of course, for the broader context of having these wormholes in the localities, it may not be necessary to have a solution. It may just be sufficient to have the topology. So I have no strong opinion whether one should base these wormholes exclusively on those which are which possess explicit solutions due to Giddings and Strominger and related to axions, or one should extend it to all such geometries where two distant points are connected by a wormhole, which maybe in principle would collapse because there's no solution, but nevertheless, as quantum fluctuations, it could contribute to the total partition function. So,
yeah, but if we think of a quantum gravity theory which doesn't arise in this way, through extra-dimensional, I mean, where you have such extra-dimensional fields, then we don't see these effects, right? Because you don't have any axion fields or other fields which can give you the charge.
Right. If you, for example, assume that only such wormholes are relevant which correspond to solutions, I mean, really solutions rather than just quantum fluctuations. And you, in addition, assume that you have no axions, which is possible, but I mean, unlikely because axions are a very simple ingredient in many situations. Then you would indeed not have such baby universes. I mean, that would certainly be one way out of the story. But I think that once you allow, in principle, topology change, then you should include such wormholes even then when they do not correspond to a solution. But that's an opinion, and it is unclear. I admit to you that there are various ways to get rid of them.
Okay, thank you.
Okay, so thank you very much for this nice talk, and